Hi everyone. Now we are going to discuss about fundamentals of algorithmic problem solving. In this presentation, we will learn how to solve computation problems systematically using algorithms. We will discuss the complete process from understanding a problem to designing, analyzing, proving correctness, and finally implementing the algorithm. So, algorithm problem solving follows several important steps. First, we need to understand the problem clearly. Next, we decide the computation approach, whether we need an exact or approximate solution, choose the suitable data structure, and select the right algorithm design technique. Then, we design the algorithm, prove that is correct, analyze its efficiency, and finally convert it into a program. If any stage is ignored, the algorithm may become incorrect or inefficient. Understand the problem. The first and most important step is understanding the problem. Read the problem statement carefully and identify exactly what input is given and what output is expected. Work through a few small examples manually to verify your understanding. Also think about special cases or boundary conditions. Remember, an algorithm should produce correct results for every valid input, not just a few sample cases. Decide on computational means. After understanding the problem, we choose the computation method. So most traditional algorithms run on a random access machine or a RAM model, where instructions execute one after another. So these are called sequential algorithms. However, modern computers may execute multiple operations simultaneously. So algorithms designed for such systems are called parallel algorithms. The choice depends on the hardware and performance requirements. Exact versus approximate problem solving. Sometimes we need an exact solution, while in other situations, an approximate solution is acceptable. An exact algorithm always produces the precise answer. An approximation algorithm provides a solution that is close enough and often much faster. Examples include calculating square roots, solving nonlinear equations, and evaluating definite integrals, where approximation methods are commonly used. Algorithm design techniques. So there are several well-known algorithm design techniques. So these include decrease and conquer, divide and conquer, transform and conquer, dynamic programming, greedy technique, backtracking, branch and bound. So each technique is suitable for different types of problems. Designing an algorithm and data structure. Choosing the correct data structure is just as important as designing the algorithm. So different data structures provide different performance. For example, C of arithmetic works much faster with an array than a linked list because arrays allow direct access to the element. So there are different ways to represent an algorithm. The simplest method is using natural language. The more common method is, we can say, the pseudocode, which is combining natural language along with the programming language construct. It is easy to understand and independent of any programming language. Another popular method is using flowchart, where geometric symbols visually represent the sequence of operations. Proving algorithm correctness. So once the algorithm is designed, we must verify that it always produces the correct output. So this process is called proving algorithm correctness. So this proof should show that for every valid input, the algorithm terminates after a finite number of steps and returns the expected result. So mathematical induction is one of the commonly used proof technique. Analyzing an algorithm. After ensuring correctness, the next step is analyzing efficiency. There are two major aspects. The first is time efficiency, which measures how quickly the algorithm runs. The second is space efficiency, which measures how much additional memory it requires. And we also consider simplicity because simpler algorithms are easier to understand, implement, and maintain. Coding an algorithm. Now we convert the algorithm into programming language. After coding, we verify the correctness through testing and debugging. Compilers can also optimize programs using techniques such as loop optimization, common sub-expression elimination, and replacing expensive operations with cheaper ones. Finally, we measure actual execution time through the empirical analysis. So these are the reference papers which is prepared for this presentation. Thank you for your attention.